Hi everyone, welcome to Numpy 5. So in this lecture we'll be discussing about these things. So what exactly is an image in Numpy? Basically it's just numerical values. Then how do we open an image? Then how do we how can we'll be seeing the details of image like shape, what are the RGB channels, etc. Then we'll be looking at how we can visualize the RGB channels. So RGB channels is what an image is basically. Every pixel is composed of these three colors. Then how do we rotate an image? Then how we can save the image, like save the image that we have rotated or something like that. Or after all these operations that we do, we can reverse an image. So reverse is basically you flip that. So you just flip the image horizontally or vertically. Then how do we crop or trim the image? So this is you could cut the borders, or you just want to see the face of it. You can just assign certain number of pixels to it, or rather cut to the pixel value that, or the pixel border that you want to crop to. Then you can blur the image. So blurring is basically you the image is composed of a lot of color values that are nearby. So what you can do is you can just take the approximate not the approximate value. Let's just say we are taking every 10th value or every 20th value. Like we I guess it's easier to show it. I'll just show the demonstration. Then how we can change image contrast. So image contrast is basically we can make it darker or we can make it brighter. So if we, as we go nearer towards the zero values, the image gets darker, and as we go towards the 255 range, it gets brighter. So let's begin. So what is an image? So image, like I said, it's just numerical values. It's a NumPy array, a three-dimensional NumPy array. If it's a color image, and if it's a grayscale image, you can just do that in 2 dimensions. Let's see how we can open the image. So let's do the first steps, the basics. Import numpy as np, and we will view the image using matplotlib. There are many other libraries, but this is the most common one. So we'll be using matplotlib.pyplot, PLOTSPLT, and I already have an image in my directory. I'll be using this image. So array equal to, we use numpy.array, and we'll use plt.imread. So we first read the image and we pass the path. So the path is the path where my Jupyter notebook is currently situated, which is in this directory. So I'll just since my my notebook is my file is in the directory where my Jupyter notebook is, I can just use the name directly, and then I can do np dot I can do plt.imshow, and then I can pass the array, the numpy array, and as you can see, we see the image. Let's call this img, and let's look at the details of the image. So it's a three-dimensional image, and as you can see, it has 30 rows, 20 columns, and three depth. The three is RGB, which is red, green, and blue channels. Every color image is generally it is a RGB standard, which has these three channels. Like I said, if it's black and white, we just need one channel, so we just need length and width. It will only be a two-dimensional array, numerical array. So currently, since we are using color, this is a color image, we have three channels. Now, let's dive deeper into what these channels are exactly. Before that, am I missing something? Right. Let's get into what RGB channels are. So as I said, RGB is red, green, and blue. Okay, I guess since this will be a theory section, I'll just show it here. So red, green, and blue. So every pixel that you see on your screen, every color pixel is basically composed of these three values or three channels, and each value in this each value is of the range 0 to 256. Now, how did we get this 0 to 256? So Numpy assigns, or internally it has a unsigned integer of 8 bits assigned for each of these values, each of the RGB values. So every red value has 0 to 256, every green value has 0 to 256, rather 0 to 255, and blue has 0 to 255. So how did this 255 come? So if we see so this red value has 8 bits assigned to it. 1, 2, okay, wait, 1, okay, 1 second. So let's call it 1, 2, 3, 4, 5, 6, 7, and 8. So we have 8 bits, so we have 8 memory locations, each can be 0 or 1, right? Binary data, so each one can be a 0 or a 1. So a 0, what is a 0 in binary? When we have 8 bits in base 10, so 1, 2, 3, 4, 5, 6, 7, 8. So if we have all ones, this is 255. The value would be 255. So if we want to represent a 0, 1, 2, 3, 4, 5, 6, 7, 8. This I'm pretty sure many of you might be knowing this, but just to cover the basics as well. Oh, sure. Let's undo. Okay. So this is a 0. So I guess I should have. Let me select this one. So this is 0. If you want to represent 1, okay. If we want to represent 1, then it will be 0, 0, 0, 0, 1, 2, 3, 4, 5, 6. Oh, sorry, 0 is all zeros. 1 would be, we represent 1, which is basically, if you see the calculation would be 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6 and 2 power 7. So we add all these values wherever there are 1 values. So if suppose we have this one here, how is this 1? This is 1 because all these values are 0. So 2 power 7 times 0 is 0, right? Say, just like that we go until 2 power 2 times 0 is 0. Then where are we? 2 power 2 is this one, and 2 power 1 is 2 power 1 is 2 power 1 times 0 is also 0, and then we get 2 power 0 times 1. This bit is 1, right? So 2 power 0 is 1 times 1 is 1. So that is how you get the first value. And here all values are 0, so we multiply all this to 0, hence it becomes 0. And just like that, if we calculate, all these are 1s, right? So if we say 2 power 0 is 1 plus 2 power 1 is 2 plus 4 plus 8, 16, 32, 64, 642 is 128. So if we add all this, you'll get 255. I hope that was clear. So maybe let me just take another value. So how do we get 2 in binary? 2 in binary is 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 of them. So 2 would be 2 power 1. So this is 2 power 0, 2 power 1. So this value has to be 1. And all these will be, so until 2 power 7, all these will be zeros anyway. 0, 0, 0, 0, 0, since these are all 0 values. 2 power 1 is 2 times 1 is 2. 2 power 0 is 1 times 0 is 0. So that's how you get 2. So that's the binary calculation here. So what were we discussing? Right, so that is how each of these RGB values contains values ranging from 0 to 255, right? So total, that is total 256. Why is it 256? Because 2 power 8 would be 255. We have to subtract minus 1. 2 power 8 number of values that this 8 bits can store. That would be 256 minus 1. Minus 1 because we start from 0, right? 0 to 255. So including the 0th value, you will have 255, the amount, you can say the quantity 255 can be stored. And from 0 to 255 quantity, this 8 bits will support. Let's see what else. Okay, we are discussing visualizing RGB channels. Okay. So, okay, now a pixel is basically RGB value combined. So each pixel is composed of these 3 values. So, and if you see a color image, you will have layers of RGB values stacked to form a R channel. This is G channel and this is B channel, blue channel. So each of these will have a bunch of numerical values for if it is an R channel. Suppose if it's an R channel, the R value will have some value like say 214, and G and B will be zeros if it's an R channel. So this is a red channel. You can say even it had, let's take 255. If it's a green channel, it will have green value and all others will be 0. And if it's a blue channel, then all others will be 0 and blue will be 255. So that is how you will see the colors. If you want to see what would be white, white is completely 255, 255, 255. It has all three values maxed out. What would be black? Black would be all zeros. So that is that's some brief theory, and there are some other, like, so RGB is not the only format for images. Like there is red, blue, green, and alpha as well. So there's RGBA, which this becomes a 4-dimensional array. So you will have R, G, B and alpha value as well set to this. Alpha is basically transparency. I think you will see that in PNG images. There are other formats as well. So basically you can have n number of channels as well. Let's just call it channels. There are n number of channels as well. For if you are suppose if it's a satellite spectral images or something like that, some advanced things can have like any number of I won't say any, you'll have more than 4 channels in that image. So yeah, so that's basic theory. So let's see how that okay, so okay, one more thing. I did say it is unsigned. Let me write it properly. Integer of 8 bits. So unsigned is basically no sign, which means no negative, meaning only positive whole numbers. So if you take only positive, let's call it only positive integers. So basically, if I create an array, suppose array equal to np dot array anywhere from, let's say 0 to 255. Let's say these are the values, and the data type would be np dot uint 8, if I'm not wrong. Yeah, so data type is uint 8. So if I suppose set a negative value here, you'll see it will throw an error. It will say conversion of -1 to uint 8 will fail in the future for old behavior usually. So it's sort of a deprecation warning, but basically uint only supports positive integers. So you should not add negative values here. And let's if we try to visualize how the image, a 3D image, or rather a color image can look a small color image. Let's create manually some pixels. So an array inside an array. Inside another array, we will have two arrays here and two arrays here. So we'll create something like red and green pixels here, and then we'll create blue and yellow pixels here. So red would be 255 0 0, green would be 0 255 0, blue would be 0 0 255. I think yellow, if I'm not wrong, is 255 255 0. Let's print this. I have to I have to pass the thing in plt dot I am show array. Yep. So we just created 4 pixels. This is a 4 pixeled image, and that's how you can set these. Or rather, this is a small demo of how images work and how RGB channels work. I think that is all there is to the basic theory. Yeah, I guess that is all there is to the theory part. Just give me a moment. I'm just thinking if I missed anything. Yeah, I guess that is all there is to it. Let's look at how we can visualize these RGB channels. Let's run this once again. We'll be using the same image, and so if I want to see just the red channel of this image, so I can take something like so if I want to see just the red, then I have to set blue and green values to 0. So we'll use masking technique, not masking exactly, we'll use slicing technique, and then we'll assign the sliced result to the to 0 value, so that so we'll take, so we want, so we are trying to index in 3D array, so we want all the rows, all the columns, but depth we only want to set green and blue values to 0. So excuse me, so 0th index is the red value. So first index and second index are green and blue. We'll set that to 0, and AMG axis. Okay, sorry, I think we have to set it to array. Array, we have set it to 0, and I think then we have to pass it to yes. So we modified the original Numpy array and then we passed it to show, and then we see only the red value. So this is how you can change it to red. Now let's try to do it for green. Let's take the same image again, and then let's do for green. So we set red and blue to 0. Wait, what did I write? So yeah, blue and green to 0, red and blue to 0, which would be 0 we wanted to set, and yeah, red and blue. So 0 and second index. 0th index is red channel, and second index is blue channel. So first index is the green channel, and we don't want to mess with that. So if you see this one, you see the green channel image. Let's do the same for blue. I don't think we have to modify or anything. I think we might have to. Let's see how this works. 0 and 1. Okay, here that will become completely black. Okay, let's get the image once again. Blue channel will set green and red and green to 0. So which would be 0 and 1. So 0th index is red and first index is green. So we are setting red and green to 0. So only the blue value remains. Now if we see the thing, we'll see the blue image. So that's how we can visualize the RGB channels. Now how do we rotate the image? Suppose, let's take the same code once again. Now if I want to rotate the image, what we'll do is we'll do a transpose. So we know, right? Transpose means shift the rows to columns and columns to rows. Let's try to do that. Array dot transpose. We'll use a special method. We can do this as well. Let's see what this gives. Array equal to array dot transpose. Invalid shape. 3. Yeah, so since this is a 3-dimensional array, we'll have to specify exactly how the transpose happens. Right, so we will use, that is why we'll use the transpose method, np.transpose, and then we'll pass the array, which is our image array that the pixel values. We'll pass the pixel values in the transpose method, and then we will set, what is it? Let's look at the axis. We'll actually pass it to the axis. Let's see the documentation once. So see, there is an axis, defaults to none. So what we'll do is we'll set the axis to we have three. It's a 3-dimensional array. So we won't be changing the dimension, right? All we want is to change the rows and columns. The dimensions will remain the same. So suppose you have a cube, like suppose this is a cube, right? So we only want to change these values, length and, so the depth remains the same. So when we are transposing, it sort of becomes like this. So if I set, so ideally the normal position is 0, 1 and 2, which is basically, if you have checked the previous classes, let me refresh once again. So if we have a 3D array, we have a length, width and depth, right? So the vertical axis is called axis 0, horizontal axis is called axis 1, the depth is called axis 2. So we also call it as, this is the first axis, this is the second axis, and depth is the third axis. So that's the naming convention. So this is the result for axis when the image is in correct order. So if you want to flip the image, what we can do is we can change the rows to columns and columns to rows, and that would rotate the image. We can also use another method called np.rot. So let's take the image again, and then we do np.rot90, and we pass the array. Then we do plt.imshow, and we pass the array 2, which is the rotated array. Let's make it clearer. Rotated. And if we see that, then the result, if you see, the result remains the same, although this rotation is slightly different from this rotation. This is rotating this way. However, this is rotating 90 degrees. So this is rotating counterclockwise, but this rotate 90 is rotating, you can say, clockwise. Or rather, okay, actually more like rotation, this is more like flipping the image, if I have to put it this way. This is rotation 1, that would be rotation 2. Let's try one more time. Now if I pass this rotated image again into, now this will be array 2, this will be rotated array 3, okay, that is rotation 90. We're back again, 1 second. If I try to rotate again, I'm getting the rotated array. This is rotated array 2. Okay, so this works better. So you can actually rotate it 90 over and over again, and we can come back to the same position. So this is basically rotation. Now, while I guess you can call this as technically rotation and flip, because when we rotate it first, it would actually go this way, and then it is, since it's changing columns to rows, it is actually flipping the image. It's doing a mirror flip as well. So if we want to do a proper what is it called, proper just clockwise rotation, then we should do this for transpose, and then what we can do is let's call this rotated image, and then we take the rotated image. We take the rotated image and we flip it vertically. So now we want to flip it vertically. So vertically is axis 0. So this one will do a start stop will remain the same and will reverse the values. Axis object is not. What is happening? Okay. I guess I'll have to take array 2. And then do a new rotation. Back to square one second. So we're doing vertically, right? Today. Oh, okay. Let me load this again. Okay, I guess I have to load this image again. 1 second. So now we have array 2. We'll pass array 2, which is okay. I have to pass array 2. So this is now the rotated image, right? So this is, you can say this is again an image. Let's check the type once. Yeah, it's an image. So we'll pass the image once again in no, I'm not sure if we can pass it directly again. Wait, let me try. Array equal to np dot array plt dot im read. We will do this, then we'll pass this array into the transpose, or rather we can just pass this array and then we'll do a plt dot show. Object has no attribute read. Okay, so I guess that's a different access. Okay, for I guess I'll have to do some research on this one, on how to flip this. I thought actually there is a way to flip this. 1 second. So if I do the flipping here itself, suppose array 2 is okay. So that as you can see, that flipped horizontally. So you can do the flip horizontally, but if we want to reflip the rotated image, then I guess np.rot is the best method for that, if we want to keep rotating the same array over and over again. So we have the rotated image, we're doing the img show, then I pass the same array. 1 second, I think it should be possible here as well. So I do array. No, this should be possible here. 1 second, since this is the rotated image. So this is the rotated image. Now I'll pass this over here. So if I do array 2 dot transpose already happened there, so 1 second, we did the transpose, which is why we got this one, right? So okay, so now this will be array 2 and then we do the show. Okay, as you can see, that is the clockwise rotation. We got the clockwise rotation. 1 second, I think bird 1 is already rotated there. Bird 1, why is it just reading PLT show? Strange. Okay, I think there is an issue with the kernel. Let me restart the kernel once. Oh, okay. I was printing array 2. That's why. Okay. So we have the original array. Now the normal image. What we can do is we can transpose this one to. So if we do just a normal transpose, it will do a. It will not do a clockwise or anti-clockwise rotation. It will do a clockwise rotation, and then it's flipping because we are changing rows and columns. Now if we want a proper clockwise rotation, we can flip the array, we can set it this way and then rotate the image. So as you can see, this became this. So it's a proper clockwise rotation. And if we want to rotate this once again, the same array, then we can take the same array and then we can do one more rotation. One second. This would be this one. Then I guess this should become this way, right? So then I guess we have to change it to. We want another clockwise, so we are flipping the give me a moment. So we are doing a transpose as a rows, columns and depth. So I'm changing the so I'm flipping the rows. Okay. We don't want to flip the rows here now. Now we'll have to do another transpose. So now array 2 would be another transpose, which would be it went back to the original. How about 0, 1? So that is the standard this one. Now if I want to flip it again, yeah, I guess what we have to do is a little bit of workaround, but what we can do is we will have to flip this. Yeah, now if I flip this to on the horizontal axis, colon -1, and then I'll have to flip it back to 1 0. So if I do a flip on the so if I flip it again, if I do the transpose again, it will flip it on the, like it will do another 90-degree rotation. So as you can see, this is a bit of a tedious process. So the easiest way would be to do np dot rot 90, and we can just flip it as many times as we want. So let's make it simpler, and we'll call this A2. We'll call it A180. This is A180. Okay, let's run this once again. So we have our original image. We rotated once clockwise 90. We rotated again clockwise 90, so that's 180. We'll do a 270 rotation. A180 will pass the previous 180-degree rotation. As you can see, that did another clockwise rotation, and then we'll do a A360. We'll pass A270 to it, and we have it back to the original position. So that's how you can rotate and flip the images. Now let's jump to we did rotating. Let's see how we can save. Saving is easy. Saving the rotated, let's say saving the image. The method is imsave. We'll use the same thing, and we'll pass the array and the specified path. Let us do this one once. So we have the rotated image, right? So if I want to do save, not np, it's plt dot imsave, and then since my Jupyter notebook is in the same, I want to save this image in the same place that my Jupyter notebook is. So let me just get rid of the previous one. So I'll call it rotated image.png, and then I'll pass the array, which is A270, and if I run it, you will see the rotated image here. And if I give it some different name, call it rot.img, and I run it again, you will see the rot.img. So that is how you save the image. Then let's check how we can reverse the image. So we have already checked reversing the image here, right? We can use the same code. Let's run this. And now if we want to reverse the image, we can do something like, now we have the rows, columns, and the depth values. The depth obviously remains the same. What we can do is we can do, let's say we want to flip it horizontally, colon, and if we pass the rotated image or the flipped image, okay, this is vertical, this is not horizontal. First is first is vertical, right? Axis 0, axis 1, then axis 2. So as you can see, this flipped it horizontally. Now if you want to flip it vertically, we just have to do it this way. So we are doing a column wise flip here. We are doing the next one was row wise flip, and then the depth we won't make any changes because those are the depth remains the same in all these cases. We are just flipping the square. So so it's something like you have the image like this. We are just flipping it this way and this way. There's no change in the depth. So that's all there is to reversing an image. We can crop as well, crop image. So cropping is if I want to say suppose I want to cut something like this over here. If I want to say suppose cut the image at this, say suppose at the 200th length and maybe at the 800th length, what I can do is I can take the array, let's do it here itself. We'll set the so this is the vertical trimming. So we'll say something like I will take the pixels at 200, we'll slice it at 200 to suppose 800, and yeah, the rest will remain the same. Let's see what the result will be. Okay, let me pass array 2. As you can see, it chopped off the pixel values from here and here. So you got a much more zoomed in, you can say zoomed in scale image. And if I want to chop off the horizontal corners, like maybe from here the 100th value and 500th value, then I can do the same again, but on the second you can say the second axis, which is I want to chop off from 100 to 500. Let's call this array 3, and we are trimming from array 2, which is from this one. So as you can see, that cropped off these extra spaces. So that's all there is to cropping. If we look at blurring, so the idea of blurring is, let me show that. So we suppose we have some pixels, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Actually, let's just take a 1D array. That will be much more easier. 1, 2, 3, 4, 5, 6, 7, 8. So if we have a 1D array, blurring, what we are doing with blurring is we are taking a how do I put it? We are taking the alternate values in a step size. So what we are doing is we are checking the step size as rows, columns, and then step size will be like, say suppose I take step size as 3. So what happens is I will take the first pixel to then third pixel, then I will take fifth pixel, then seventh pixel. I will only take these pixels, and rest others I will discard. So that scales down the image, scales down the number of pixels, but we will still be able to see an approximate image value. I hope I made the point clear. So let's take the same image again. Now if I want to blur the image, let's see, I will take the array values and start stop will remain the same, but step size will be 0. I mean start stop will be the entire image. Step size will be for the columns. Let's say I want to do a step size of 30. Same for top and bottom, and depth we won't be touching. Now blurred image, and then plt.im show. I pass the blurred image. As you can see, the image got significantly blurred. Let me show. Let me do slightly less sample down, maybe about 10. So 10, as you can see, 10 is we can still see the image. I mean, we can still like figure out that it's the same image, but it's extremely pixelated because we have if I show an example here, we have taken a pixel from here, then a pixel from here, then a pixel from here, then a pixel from here, and then we have discarded all other pixels. So that has compressed the image, so it's only taking the approximate value. It does not have all the details. That's exactly what it is. That's what a blurred image is, and that's all there is to blurring. Let's look at image contrast, or rather before that let's look at grayscale. Grayscale image. Actually, image contrast only. Let's check image contrast. There is negative contrast in image contrast, so we can check that. So image contrast, basically what we will be doing is I'll be setting an approximation where I'll be blowing up the contrast to maximum. So I'll make the image extremely bright. So I'll keep all the bright values, and I'll try to reduce all the suppress all the darker values. So what I can do is I will take the array. I'll call it array2, and what I will do for all values greater than 150. Okay, I have to do np dot where array values greater than, for all values greater than 150, I will set the values to maximum, and all others I will set it to 0. So if I do a plt dot im show array2, you see it literally removed all values that are less than 150. So I've set all that to 0, and all values greater than 150 we set it to maximum. So that is why that's you can say positive contrast. Now if we try to do a negative contrast, like the ones you see in negative films, for when you take a photograph in those analog photographs, that one, what we can do is we can subtract all the values from 255. So array3 so we have subtracted all the values of the image from 255. Okay, 1 second. I guess I have to run it once again. So I ran it once again because now we are borrowing this image. Let's borrow the original image. So that's the negative film. So this is how you can do image contrasting, and that is it for today. Okay, before that, in the previous Numpy 4 section, there was one issue we faced, right, which was the object array. Object array, object Numpy array, the memory location issue. So the problem was Numpy object array, if we are creating an values greater than 256 in the object array, they will all be allocated same memory location if it is created within the array. If you are assigning it, if you are updating the array separately, then new memory locations are created if the value is greater than 256. So we know that Numpy uses CPython, right? We have discussed in the 4th class, and the range of values for memory reuse is -5 to 2. I guess it was 255 or 256. I think it's 255 only. No, 256. 255 to 256. So suppose let's create an array here, object array, np.array. If I give values greater than 256, say I give 10,000, 10,000 here, 10,000 here, and I give 256, I give -100, and I give -5, -4 as well. Let's give a 255 as well. So let's create another -100. And we set the D type to object. So if we look at the ID of first element, it is something like this. Now if I compare ID of 1 and 2, index 1 and 2, elements at index 1 and 2, you see they both are same. So Numpy is reusing values within the array when it's created. Now if I suppose update the array, let's say I do array 0, I give it a value of 4,000. Let's print the array. The value is 4,000, it got updated. Now if we check the same over here, actually let's update both. So you see, before the updation, both of them had same value, but after the update, both memory locations are different, even though the array, let's print the array, even though the array has same values now. So, but if I give values 256 or maybe less than 256, you see it has the same memory. If I give less than 256 or suppose 256 or even 10, it's still, both of them retain the same memory. So that's the catch there. If you are updating the value and if the values are greater than 256, Numpy creates separate memory, allocates separate memory for each of those values. But if it is less than 256, then it will reuse the same it will reuse from the same memory. You can force NumPy to reuse the same thing using special methods, but that we can discuss sometime later on, but that is also an option. So that is all for NumPy 5. I hope some things are clear. Thank you, and I'll see you in the next one.